If you have ever stared at one of those deep space photographs, the kind that looks like someone spilled a bag of glowing marbles across the darkest table imaginable, you might assume the universe is jam-packed with stuff. Galaxies stacked on galaxies stacked on galaxies, like cosmic traffic during rush hour with far more style and far fewer impatient honks. But that image hides a secret, because for all the celestial glamour squeezed into a single frame, the truth is that most of the universe is emptier than a teenager's fridge 20 minutes after payday. It is a quiet, enormous, invisible gulf that stretches between galaxies, a place so vast and so underpopulated it makes the loneliest desert seem like a Saturday market. And today, we are diving headfirst into that void, not because we enjoy loneliness, but because that empty darkness is not nearly as empty as it looks. Good evening, curious minds. I truly hope you will enjoy today's video. Before we begin, leave a comment and tell me where and when you're tuning in. And if you find yourself learning something new as you drift toward sleep, consider subscribing, but only if you enjoy these calm journeys through the universe. Now, let's begin. It is funny how space photography tricks us. A long exposure shot can make galaxies look like they are holding hands, huddling together for warmth in the cold of eternity. But zoom out just a bit. No fancy telescope, just a mental zoom out, and suddenly each of those glowing spirals, ellipses, and chaotic star swarms is floating alone in a truly massive ocean. The distances between them are so huge that if you could drive a spaceship the way you drive a car, you might give up and take a cosmic bathroom break before you even left your home galaxy's neighborhood. When astronomers say empty, they mean the kind of empty where you could travel for millions of years and still be asking, "Are we there yet?" into a microphone no one else can hear. But here is where it gets interesting. The space between galaxies is not just a big blank nothingness waiting for a decorator. Something lives there. Many somethings, actually, even if they are spread out so thinly that calling them neighbors feels like a stretch. And that is the heart of this cosmic mystery. If the universe is mostly emptiness, why does that emptiness matter so much? Because understanding what fills the space between galaxies is like reading the fine print of reality. It is quiet, subtle, and it contains the clues to how galaxies form, how they evolve, and how all the material in the cosmos is connected in ways we can barely wrap our human-sized brains around. The funny thing about intergalactic space is that the word nothing does not quite cut it. Nothing is what you call the place where your socks vanish in the dryer. Intergalactic space is more like the universe's attic, dusty, scattered with forgotten objects, and full of strange currents and drafts that do not quite make sense until you poke around for a while. It is a region almost nobody notices, because the big glowing galaxies steal the spotlight like prima ballerinas twirling center stage. Yet the real structural support, the invisible scaffolding that allows galaxies to even exist in the first place, stretches out into that dark, quiet space, binding and shaping the cosmos in ways we are still working to uncover. And maybe that is why this topic hits so hard. It is not just about science. It is about perspective. We humans love focusing on the bright, flashy things, the stars, the nebula, the spectacular explosions that make headlines. But the universe reminds us again and again that the spotlight is not where the real story ends. The stuff in between, the vast quiet spaces that seem boring at first glance, are essential chapters in the grand cosmic novel. If galaxies are the characters, then the intergalactic void is the setting that shapes their journeys, nudges their fates, and silently connects them across unfathomable distances. So the next time you see one of those gorgeous galaxy-filled images, remember this. It is a bit of a cosmic illusion. Those glowing jewels may look close enough to clink glasses, but in reality, they are separated by expanses so big that calling them distances feels inadequate. They are divided by gulfs that swallow light, time, and imagination with equal ease. And within those gulfs exists an entire hidden world, a world we rarely talk about, but that might be more important than the galaxies themselves. This journey into the space between galaxies is not just a tour of emptiness. It is an exploration of the subtle, the faint, the nearly invisible things that hold the cosmos together. The universe may look crowded from afar, but if you step into the darkness and let your eyes adjust, you will discover that even the emptiest regions are quietly alive, carrying secrets that stretch far beyond the light we see. And that is where our story begins, right in the middle of the vast cosmic silence that is not as silent as it pretends to be. If you ever wanted to know what true emptiness feels like, you would not look at a blank wall or an unplugged refrigerator, or even that awkward silence during a group video call. No, the gold medal for emptiness goes to intergalactic space, a region so profoundly deserted that calling it lonely is almost an insult to loneliness. This is the wilderness between galaxies, a frontier so big and so devoid of company that even tumbleweeds would file a complaint. And yet, for all its emptiness, it is not a perfect vacuum. Not quite. There are things out there, scattered with a reluctance so intense it feels like the universe forgot to clean up after itself. Imagine taking the driest desert on Earth, the kind where even the cacti look like they are reconsidering their life choices, and zooming way out. Desert air, as empty as we think it is bustling compared to intergalactic space. In the desert, you have dust, microbes, the odd beetle doing whatever beetles do, and of course enough air molecules to fill your lungs with something other than existential dread. But between galaxies, the number of particles per cubic meter might be so low you could count them faster than you could make a sandwich. And not even a complicated sandwich, just bread and maybe a slice of cheese if the fridge is feeling generous. Yet this emptiness is part of what makes intergalactic space so fascinating. It is not empty in the way an abandoned building is empty. It is empty in the way a massive, ancient landscape is empty, vast, quiet, and shaped by forces that move slowly, patiently, and with absolutely zero regard for our impatience as a species. You can think of it as the universe's version of untouched wilderness, the stretches where nature does not care who is watching. There are no streetlights, no gas stations, no cosmic signposts saying, next galaxy in 5 million light years, just a boundless abyss dotted with the faintest traces of material, drifting with no schedule and no hurry. Calling it a wilderness is not poetic exaggeration. Intergalactic space has weather of a sort, though not the kind that gives you rainstorms or wind that ruins your hair. It has massive zones where gravity subtly pulls material into delicate patterns, creating flows so faint and so stretched out that they make regular space look busy. If you want drama, this is slow burn drama, the kind where change happens over billions of years. It is like watching a glacier move, except the glacier is made of almost nothing, and the movement is measured in distances that make your brain quietly tap out. But despite being almost empty, this region still refuses to be an actual vacuum. A vacuum, in the purest sense, is a space completely devoid of matter. Nothing there. Nothing at all. Intergalactic space flunks that definition because even here particles drift with extreme patience. A few atoms of hydrogen here, maybe a lonely helium atom over there. In some places, you might find a whisper of ions or a smudge of electrons that parted ways with their atoms long ago. These particles are so sparse, they might never collide with each other for thousands or even millions of years. This is not a crowd. This is a cosmic whisper, a place where matter is so spread out, it seems allergic to company. And yet for astronomers, this sparse wilderness is a treasure trove, because every tiny particle floating there, every faint stretch of material, is holding the memory of events that galaxies have forgotten. Radiation passes through these vast regions, occasionally bumping into a particle and leaving behind a signature so faint it is like finding a fingerprint smudged on a window no one has touched in a century. Studying these traces helps reveal how galaxies behave, how they move, and how they shape the space around them. The wilderness between galaxies becomes a diary written in the faintest ink, legible only to those willing to spend years decoding it. Intergalactic space also teaches us something unintentionally profound. It reminds us that emptiness is not the same as absence. Just because something is nearly empty does not mean it is unimportant. In fact, the very sparseness of intergalactic space helps maintain the separation that lets galaxies exist without tearing each other apart every other Tuesday. The wilderness is a buffer zone, a space that keeps the cosmic peace by simply being there. Large, quiet, and almost completely devoid of trouble. But perhaps the most remarkable thing about this cosmic wilderness is how it challenges our sense of scale. We humans walk around on a planet that feels huge, spin around a star that feels even bigger, and admire galaxies that seem impossibly vast. Then we learn that the space between those galaxies is even bigger still, so big that a galaxy could drift through it for billions of years without getting anywhere close to a neighbor. It forces us to rethink what large and empty really mean. It forces us to acknowledge that the universe does not do anything halfway. When it creates emptiness, it commits. Intergalactic space is where the universe stretches out, relaxes, and shows us just how enormous reality truly is. It is the cosmic wilderness, raw, quiet, patient, and full of secrets, waiting for us to notice them. If intergalactic space is the great cosmic wilderness, then the atoms floating inside it are the shy wanderers who showed up, glanced around, decided this was not their scene, and immediately scattered as far from each other as possible. These atoms, mostly hydrogen, sprinkled with a little helium and the occasional rare trace of something heavier, are the universe's wallflowers. They drift through the darkness with the slow confidence of beings who have nowhere particular to be and several billion years to get there. If galaxies are the universe's bustling cities, then these atoms are the lone hikers, wandering the countryside, taking the scenic route across distances so unimaginable they start to feel philosophical. Hydrogen is by far the star of this strange, dimly lit show. But calling it a star might be giving it more excitement than it actually experiences in the intergalactic void. Inside a galaxy, hydrogen leads an eventful life. It collides with other hydrogen atoms, forms clouds, participates in star formation, gets blasted by radiation, sometimes becomes part of a cosmic structure, sometimes part of a star, sometimes part of a person wondering what intergalactic hydrogen is doing right now. But outside galaxies, hydrogen is the quiet kid who moved out to a remote cabin and checks the mailbox once a decade. To understand how lonely these atoms are, imagine a single hydrogen atom floating inside a cubic meter of intergalactic space. Now imagine another hydrogen atom several meters, or in many cases, several kilometers away. These two atoms might never meet, not because they dislike each other, but because the universe has placed them in an arena so ridiculously large that even light, the universe's speed champion, takes its sweet time crossing it. If intergalactic hydrogen had a social life, its status would read something like active one collision every few million years. Despite their solitary existence, these atoms are not doing nothing. They move with the slow, steady energy left over from the early universe. Many of them have been drifting for more than 13 billion years, untouched, unbothered, and unincorporated into anything dramatic like a star. They are the cosmic equivalent of someone refusing to join group projects for an entire semester and still graduating on time. These atoms have seen the rise of galaxies, the collisions of enormous clusters, and the glow of ancient light washing past them. They are witnesses to the grand story of the cosmos, but they do not participate. They simply drift. But what makes these atoms especially interesting is that they carry memory in their very existence. The hydrogen atoms floating between galaxies are often leftovers from events that were once extraordinarily violent. Some may have been blasted out of galaxies by supernova explosions. Others might have been pushed out by powerful jets streaming from active galactic centers. Some were stripped away during galaxy collisions, tossed into intergalactic space like debris carried off by a cosmic undertow. And a few have been floating freely since the dawn of the universe, never captured by any galaxy's gravity, never heated by any star, never part of anything larger than themselves. Imagine that. An atom that has spent its entire existence alone, untouched, since shortly after the universe cooled enough for atoms to form in the first place. That is not just a loner. This is solitude so extreme it becomes impressive. These atoms are the minimalists of the universe. They do not need a galaxy. They do not need a star. They are perfectly content drifting through the darkness, minding their own business while galaxies argue, collide, and explode in the distance. And even though they are sparse, they are far from irrelevant. These intergalactic atoms can be detected through the faintest absorption lines they imprint on the light that passes through them. When the light from extremely distant galaxies or quasars crosses intergalactic space, these lonely atoms leave tiny notches in the spectrum, a sort of cosmic Morse code. Astronomers decipher these tiny dips in brightness to map where the atoms are, how they are moving, and what conditions they live in. It is like eavesdropping on the quietest group in the universe, one atom at a time. Their existence also reveals how uneven and dynamic the universe really is. Even though these atoms are spread out like guests who refuse to attend the party, they still trace enormous structures, subtle, delicate boundaries sculpted by gravity over billions of years. Large-scale patterns, faint flows, and drifting currents all reveal themselves through the behavior of these solitary atoms. They may be sparse, but they are storytellers, carrying information that galaxies themselves sometimes obscure in their noisy, bright environments. In a strange way, these atoms are the universe's long-term travelers, the ones who take the back roads instead of the highways, the ones who see everything even if they never settle down. They remind us that not all matter participates in the grand, dramatic events we associate with cosmic evolution. Some matter chooses a quieter path. And that quiet path, stretched across billions of light years, helps us understand the subtle fabric of the cosmos, not through spectacle, but through persistence. So the next time you imagine intergalactic space, do not picture a perfect vacuum. Picture a scattering of ancient hydrogen atoms drifting peacefully like cosmic introverts, each one carrying a tiny piece of the universe's history as it glides through the darkness, far from any galaxy's noise, content to exist in solitude. If the lonely hydrogen atoms drifting through the cosmic void are the quiet wanderers, then the warm, hot intergalactic medium is the simmering broth they sometimes find themselves floating in. This medium, often called the warm, hot intergalactic medium, though scientists say it fast enough to sound like a single, long sigh, is one of the universe's more peculiar features. It is not dense enough to be a cloud, not hot enough to be a star, not cold enough to be empty, and not structured enough to be anything comforting. It is a diffuse, heated soup of gas stretching between galaxies, threading itself across the cosmos like faint, glowing embroidery you can barely see unless you squint extremely hard or point a billion-dollar observatory at it. To appreciate just how strange this medium is, you have to imagine a gas so thin that you could carve out the volume of an entire star and still barely collect enough material to fill a thimble. Yet the little bit that is there is heated to temperatures that make the surface of the sun look like a pleasant summer afternoon. The warm, hot intergalactic medium exists in a curious temperature range. Not warm like bathwater, not hot like molten lava, but something in between. Warm-hot is a scientific term that politely sidesteps the fact that this gas is heated to several 100,000 to several million degrees. If it had a personality, it would be the quiet kid in class who casually mentions they climb active volcanoes on weekends. This medium forms delicate filaments, cosmic rivers of energized gas that stretch between galaxies. These filaments are not visible to the naked eye or even to most telescopes. They are so faint, so stretched thin, that astronomers sometimes joke they are trying to observe the universe's ghost fog. But this ghost fog matters. In fact, it matters so much that scientists spent years hunting for it like detectives trying to solve a cosmic cold case. The mystery of the universe's missing normal matter. Yes, missing. As in, the universe misplaced a significant chunk of its ordinary matter, the regular atoms that make stars, planets, pizza, and every questionable decision a human has ever made. When astronomers added up all the matter in galaxies, stars, and gas clouds, they found that about half of the expected normal matter simply was not accounted for. Not dark matter, not mysterious exotic particles. Normal matter. Protons, neutrons, electrons. The everyday stuff. It was as if the cosmos had written a grocery list and forgotten to buy half the items, then pretended everything was fine. Enter the warm, hot intergalactic medium, the universe's version of a messy attic where things go missing for billions of years. Over time, astronomers realized that this heated, diffuse gas might be harboring the lost matter. The problem was detecting it, because looking for the warm, hot intergalactic medium is like trying to find fog made of warm breath in an already foggy room. The gas does not shine brightly. It does not form structures that cameras can easily capture. Instead, it leaves tiny signatures, whispers in the data. To detect this medium, scientists tracked how light from distant objects changes as it passes through the intergalactic soup. Imagine shining a flashlight through a cloud so thin you can barely tell it is there, yet the light still picks up microscopic clues. The warm, hot intergalactic medium leaves subtle fingerprints on the radiation that crosses it, slightly bending or absorbing specific wavelengths. These faint marks are the cosmic equivalent of someone leaving a smudged thumbprint on a window. Hard to find, easy to ignore, but unmistakable once you know what to look for. And those fingerprints point to a fascinating truth. The missing normal matter is not missing at all. It is just lounging in the warm, hot intergalactic medium, stretched thin across the universe like a cosmic, lazy river. It did not disappear. It simply refused to assemble into galaxies, preferring instead to drift in the wide open spaces between them. This gas is one of the great connectors of the cosmos, forming threads that tie galaxies together into vast networks. It is the quiet infrastructure that nobody sees but everyone depends on, like the plumbing inside a building or the cables under a city street. The warm, hot intergalactic medium also reveals how turbulent the space between galaxies can be. Though it might seem peaceful at a glance, This medium is constantly stirred by the push and pull of gravity, by shock waves from galaxy collisions, and by enormous jets launched from supermassive black holes. These events heat and move the gas, shaping its distribution into intricate patterns that help map out the skeleton of the universe. The medium is a witness to cosmic events on scales we can barely imagine, events so vast and subtle they unfold over billions of years. And despite its quiet faintness, this medium holds a kind of understated drama. It is the battleground where galaxies exchange matter, the pathway where material drifts across unimaginable distances, and the hiding place of ancient atoms that escaped their galaxies long ago. It is hot enough to shine in certain wavelengths if you know where to look, yet so diffuse that nothing about it behaves the way gas normally does. This is gas living its most non-committal life, refusing to form stars, refusing to settle into galaxies, and refusing to be easily found by anyone. In uncovering this strange, heated mixture, scientists solved one of the universe's longest-standing mysteries: the location of the missing normal matter. And in doing so, they uncovered a vast, invisible web that connects the cosmos. The warm, hot intergalactic medium may be sparse, but it is one of the quiet engines of cosmic structure. A simmering soup that tells us where the universe hides its forgotten ingredients. If you could step outside the universe and look at it the way you might study the pattern of frost on a window, you would see something astonishing. A sprawling network of threads and empty bubbles stretching across hundreds of millions of light years. This colossal arrangement is known as the cosmic web, though web might be too delicate a word for something that could wrap around trillions of stars and not even break a sweat. It is the architecture of the universe on its grandest scale, a design so enormous and intricate that no human mind can fully picture it, yet simple enough in principle to be shaped by only two ingredients: matter and gravity, working together like an invisible cosmic 3D printer that never runs out of filament. The cosmic web is not made of string or silk, of course. Its threads are composed of galaxies, gas, and even the faintest traces of matter stretched thin across the dark. These filaments weave between gigantic empty regions known as voids, cosmic bubbles that contain almost nothing except the quiet whisper of atoms passing through. Voids are not holes. They are enormous spaces where gravity has simply chosen not to gather much material. The result is a universe built from contrasts: extreme emptiness next to surprising density, quiet zones bordering crowded intersections where galaxies cluster together as if comparing notes on their journeys. To understand how the cosmic web formed, imagine the early universe as a calm sea of matter that was almost, but not perfectly, smooth. In that near-uniform sea, some regions had a slightly higher density than others. Those tiny variations became the seeds of everything that followed. Gravity, being the universe's most stubborn sculptor, pulled matter toward the denser spots, slowly growing them over billions of years. It did not rush. It simply tugged, nudge by nudge, like a patient artist coaxing clay into shape. Where matter collected, filaments formed. Where matter drained away, voids opened. And as this process continued, the entire universe developed a network so vast that even our fastest spacecraft would need many lifetimes to cross just one of its strands. What makes this structure especially mesmerizing is how the empty spaces between galaxies play an essential role. Those enormous gaps, so barren they make the idea of isolation seem cozy, guide the flow of matter just as much as the filaments themselves. Think of the voids as the negative space in a sculpture. They do not just accent the artwork, they define it. As matter streams inward from these empty regions, it funnels into the filaments, thickening them over time. The filaments then channel that matter into dense nodes, where galaxy clusters form, creating intersections that can hold thousands of galaxies bound together in a gravitational handshake. In this sense, the universe behaves like a cosmic printer, shaping three-dimensional structures using gravity as the guiding mechanism and the vast emptiness as the mold. Instead of plastic or metal, the filament material is matter, some visible, some invisible, flowing into place with the grace of an impossibly slow river. And because this process never truly stops, the cosmic web is always under construction. Every filament is gently thickening, every void slowly widening, every cluster gradually gathering more galaxies, like a host collecting guests at a never-ending banquet. The scale of these structures is almost beyond comprehension. A single filament can stretch hundreds of millions of light years, yet be so faintly packed with galaxies that it would be hard to notice without the help of powerful telescopes. These strands are not neat, uniform lines. They twist, branch, reconnect, and drift, forming a network that looks less like a spider web and more like the neural wiring of a cosmic brain. Meanwhile, the voids between them can be unimaginably vast, spanning distances so great that if you placed a galaxy inside one, it would float in isolation for billions of years before stumbling upon a neighbor. The cosmic web also reveals how interconnected the universe truly is. A galaxy is not an island. It is part of a filament, which is part of a larger structure, which eventually connects to a network spanning the observable cosmos. If you tug on one region, say through the gravitational collapse of a cluster, the effects ripple outward over time, subtly influencing nearby strands. Even the most remote galaxy is plugged into the web, participating in its slow dance, whether it realizes it or not. Astronomers study this vast network using a combination of observations and simulations. Mapping the web directly is tricky because most of it does not shine brightly. But by analyzing how galaxies cluster and how matter bends light as it passes by, scientists can reconstruct the filaments and voids like forensic artists recreating an enormous cosmic crime scene. Computer simulations take this further, generating models where the universe evolves from its early smoothness to its present-day complexity. These simulations show filaments forming naturally, branching out exactly the way real observations suggest. It is like watching the cosmic 3D printer in time-lapse, one that takes billions of years to complete a project, but never loses accuracy. What makes the cosmic web so captivating is that it represents the universe's hidden scaffolding. It is the blueprint underlying everything we see, the pattern that dictates where galaxies grow, where stars ignite, and where cosmic emptiness settles into place. Without these filaments guiding matter into structure, the universe might have remained a bland soup of particles spread evenly in every direction. Instead, gravity pulled threads from that soup, sculpting a masterpiece whose scale dwarfs human imagination. In the end, the cosmic web is the universe's grand design, an intricate network sculpted by the quiet spaces between galaxies, shaped by gravity's patient hand, and printed across the cosmos on a scale so awe-inspiring that even the boldest metaphors struggle to keep up. It is the architecture of existence itself, woven from matter, stretched by emptiness, and quietly holding the universe together, one filament at a time. When we talk about dust on Earth, we usually mean the stuff that gathers on bookshelves, clings to forgotten corners, and causes sneezing fits at the worst possible moments. Intergalactic dust, however, is in a completely different league. These are microscopic grains that have escaped the cozy gravity wells of galaxies and embarked on epic, multi-billion-year vacations through the great cosmic outdoors. Each tiny grain is essentially a microscopic tourist with no itinerary, drifting leisurely between galaxies at a pace so unhurried it makes glacial movement look like a sprint. To appreciate what makes intergalactic dust fascinating, you need to understand just how improbable its existence is. Dust in galaxies gets tossed around constantly, shoved by radiation pressure, swept into star-forming clouds, heated by nearby stars, and sometimes blasted into oblivion by supernova explosions. It is not a peaceful lifestyle. So how does any of it end up floating between galaxies in the most remote real estate the universe has to offer? The answer lies in the rare dramatic events that push dust outward with enough force to escape a galaxy's grip. One of the biggest culprits is the supernova, a dying star's explosive farewell that throws dust grains into space with tremendous speed. Not all grains survive the blast. In fact, many are destroyed on impact, shattered like microscopic bits of glass. But the stubborn ones, the resilient grains that hold together through shock waves and turbulence, can be flung so far that they break free entirely. Once these grains drift beyond the galaxy's outskirts, gravity loses its persuasive charm, and the grains begin their long, unplanned journey into the open intergalactic wilderness. Another pathway for dust escape comes from intense outflows generated by supermassive black holes. These objects, sitting in the centers of galaxies, occasionally launch jets and winds so powerful they can sweep dust outward like a cosmic leaf blower set to maximum. The dust caught in these winds can be carried far beyond the visible structure of the galaxy, expelled into intergalactic space where it slows down, cools off, and starts wandering without supervision. Once dust grains reach the intergalactic medium, they behave like slow-moving tourists who left home without a map. They drift and drift and drift, following gentle currents of gas or the gravitational nudges of nearby matter. A dust grain in this environment could travel for millions of years without encountering anything more interesting than a few stray photons and the occasional faint breeze of charged particles. If grains had personalities, these would be the introverts of the cosmos, perfectly content in their solitary journeys, unbothered by the fact that they may not meet another solid surface for half an eternity. These grains are tiny, far smaller than a grain of sand, yet surprisingly important. Their chemistry is rich and complex. Many are made of carbon-based compounds, silicates, or metallic elements forged in previous generations of stars. In a poetic twist, the dust wandering between galaxies is literally stardust, the recycled remnants of ancient suns that ended their lives long ago. Some grains may have originated billions of years in the past, surviving galaxy collisions, stellar explosions, and long currents through intergalactic medium. They carry within their structures a kind of cosmic autobiography, etched atom by atom. Despite their miniature size, these intergalactic dust grains can leave discernible fingerprints on the universe. When they drift in front of distant galaxies or the faint glow of the early cosmos, they can subtly dim or redden the light passing through them. This effect, known as extinction, is like looking at the universe through a very slightly smudged window. For astronomers studying faint, faraway objects, even the smallest amount of dust can complicate observations. A grain may be small, but when you multiply it across millions of light years, the influence becomes noticeable, like the cumulative effect of tiny scratches on a camera lens. What makes intergalactic dust especially intriguing is not its abundance, because it is rare, but its endurance. Dust inside galaxies lives a rough, short life. It gets destroyed frequently, recycled quickly, and absorbed into new stars or planets. But dust between galaxies enjoys something close to cosmic retirement. There are no turbulent star-forming regions out here, no supernovae firing at point-blank range, no black holes stirring the environment like cosmic blenders. The intergalactic wilderness is harsh in its emptiness, but gentle in its lack of activity. A dust grain. Some stars live their entire lives quietly orbiting within the boundaries of their home galaxies, behaving themselves, following the cosmic rules, and never venturing beyond their assigned neighborhoods. And then there are the other stars, the rebellious ones, the cosmic dropouts, who get kicked so hard by gravitational chaos that they fly out of their galaxies entirely. These are the rogue stars, solitary wanderers drifting through the dark gulfs between galaxies, like dramatic quitters who slam the door on their home systems and never looked back. To understand how a star becomes a rogue, imagine the most chaotic group project in the universe, a galaxy filled with billions of stars tugging on each other through gravity. Most of the time, the stars settle into stable orbits, moving gracefully like dancers in a slow-motion waltz. But every now and then, the music stops, the lights flicker, and gravitational forces lose their delicate balance. This can happen during galaxy collisions, close encounters between stars, or interactions with the monstrous gravitational fields of supermassive black holes. In these cosmic mosh pits, a star can receive a gravitational shove strong enough to eject it at speeds so high it breaks free from its galaxy's gravitational grasp altogether. One of the biggest offenders in producing rogue stars is the supermassive black hole lurking at the center of most large galaxies. When a binary star system strays too close, the black hole can grab one star and fling the other outward with such force that it is launched into intergalactic space. This scenario is known as the gravitational slingshot, though it works less like a playground toy and more like a high-stakes cosmic catapult. The star that gets ejected rockets away at blistering speeds, sometimes fast enough to escape not just the galactic center, but the entire galaxy itself. It is the astrophysical equivalent of being kicked out of a nightclub with enough momentum to cross the entire city. These stars, once ejected, enter the vast wilderness between galaxies, a realm with no bustling stellar neighborhoods, no bright clusters, and no orbiting companions to keep them company. A rogue star drifts alone through shadows so deep that a single spark of starlight is nearly the only evidence of its existence. It is not entirely dark out there, but the environment is so sparsely populated that the star effectively becomes a glowing hitchhiker on a highway that stretches across millions of light years. Despite their isolation, rogue stars do not stop shining. They continue burning their fuel the same way they did back home. A massive rogue star might blaze brightly for millions of years before going supernova in utter solitude, detonating in a place where no galaxy watches and no cosmic neighbors gather to gossip about the explosion. Smaller stars may glow for billions of years, drifting slowly through the silent dark, never encountering another stellar system. Their journeys are so long and lonely that even light, the fastest traveler in existence, might take tens of millions of years to reach anything interesting. What makes rogue stars especially fascinating is how they reveal the violence and unpredictability of galactic environments. Galaxies often look serene in photographs, swirling elegantly like luminous cosmic pinwheels. But beneath that elegance lies a world of gravitational tension, where stars tug and pull with enough force to bend orbits, redirect gas flows, and occasionally send objects flying. Rogue stars are the aftermath of these invisible battles. Their very existence is proof that galaxies are not quiet suburbs, but dynamic, restless landscapes shaped by constant motion. Some rogue stars form during galaxy mergers, when two enormous collections of stars crash together in slow but dramatic interactions. As the galaxies weave around each other, their gravitational fields warp and twist like dueling whirlpools. Stars caught in the wrong place at the wrong time can be slung out like stones from a slingshot. Once launched, they drift into the intergalactic gulf, carrying with them chemical clues about the galaxy they once called home. To astronomers, these stars are cosmic migrants, telling stories about the galaxies that birthed them. Some planets orbit their stars with loyalty, sticking close to their gravitational parents, like well-behaved students following a field trip, chaperone. And then there are the others, the cosmic strays, the planets that drift through the universe with absolutely no star, no solar system, and no itinerary. These are the wandering planets, the free floating worlds that slipped away from their home systems and now drift through the intergalactic darkness like students who lost the group during a museum tour and decided to explore the city on their own. What makes these worlds especially fascinating is that they were almost certainly born in ordinary star systems. They started out like any other planet, orbiting a host star, settling into their roles, and maybe being part of a lovely little planetary family. But star systems, despite looking serene from afar, are chaotic places. Young stars often form in crowded clusters where gravitational forces push and pull like elbows in a tightly packed crowd. In this chaos, a planet can easily be jostled out of its orbit. If the gravitational shove is strong enough, the planet can be ejected entirely, flung out into space with no hope of returning. It is a cosmic, accidental exit. Except once you leave the star, the universe does not offer a lost and found desk. Other times, wandering planets are thrown out during planetary sibling rivalries. When massive planets form and migrate through a system, their interactions can destabilize smaller worlds. These interactions are slow-motion collisions of influence, gentle gravitational nudges that gradually grow into planet-flinging drama. Eventually, one unlucky world might be catapulted out of the system altogether. If planets had inner monologues, this one would be muttering, "I was literally minding my own business," as it drifts into the cosmos. Once a planet becomes a wanderer, its environment changes dramatically. Instead of orbiting a warm star, basking in gentle radiation, and having predictable days and seasons, the planet is plunged into darkness colder than anything imaginable. There is no sunrise, no sunset, no neighboring planets shining in the sky. The universe around it becomes a silent and endless night, illuminated only by distant stars so far away they offer no warmth and hardly any light. A wandering planet does not orbit anything anymore. It simply falls endlessly through the fabric of space-time. You might imagine these planets as barren, frozen marbles drifting through the void, and some of them certainly are. But the surprising truth is that a wandering planet does not have to be dead or featureless. If it formed with enough internal heat, perhaps from gravitational compression or radioactive elements in its core, it could maintain a warm interior long after being ejected from its system. Some planets might even harbor subsurface oceans beneath thick crusts of ice. Locked away from starlight, but warmed from within, these oceans could persist for millions or even billions of years. In the vast cosmic dark, life on such a world would not look toward the sky. It would thrive in complete absence of a sky at all. Detecting wandering planets is one of astronomy's most challenging tasks. They do not emit light. They do not reflect the glow of a nearby star. They are, for all practical purposes, cosmic ninjas, stealthy, silent, and nearly invisible. The few that have been detected were found through gravitational microlensing, a phenomenon where the planet's gravity briefly magnifies the light of a background star as it passes in front of it. This effect is tiny, fleeting, and incredibly rare, which is part of why wandering planets remain some of the most mysterious objects in astronomy. For every one we detect, there may be thousands or millions drifting unnoticed. The numbers are staggering. Some models suggest that free-floating planets might actually outnumber stars. Imagine that. The universe might have more homeless worlds than it has suns. Entire planets silently slipping through the darkness, never bound to a star, moving without direction except for the faint gravitational influences of the galaxies they pass. It is a strange thought that the cosmos is filled with planets we will never see, planets that have been on their lonely journeys since before Earth even existed. These wanderers may occasionally pass through the outskirts of galaxies, coasting along the gravitational boundaries like travelers checking the view from a scenic overlook. But even when they enter a galaxy, they are unlikely to join a new star system. The odds of a planet being captured by a star are unbelievably low. Stars do not go around adopting stray planets easily. The gravitational choreography required for capture is precise and rare. Most wanderers simply drift through, taking in the cosmic scenery before heading back out into intergalactic space. If a wandering planet had a sense of humor, it might describe its existence as the ultimate road trip. No map, no speed limit, and no annoying backseat drivers. It just rolls with the emptiness, traveling distances that defy imagination. These worlds are cosmic minimalists, carrying only their internal heat and their long histories as they float through the universe. But despite their solitude, wandering planets remind us of something profound. The universe is filled with objects that defy our expectations. Worlds do not need stars to exist. They do not need orbits to persist. They do not need sunlight to hold onto secrets. A wandering planet is proof that the cosmos is far stranger and more unpredictable than the tidy diagrams in textbooks. It is a universe where even planets can lose their group during the field trip, choose not to panic, and simply keep drifting through the dark, absorbing the quiet, embracing the unknown, and exploring the intergalactic wilderness on the longest, loneliest adventure imaginable. Black holes usually come with a certain territorial vibe. They sit at the centers of galaxies or lurk inside stellar neighborhoods, quietly consuming matter the way a vacuum cleaner inhales dust bunnies. But every so often, the universe decides to perform a trick worthy of a cosmic magician. It boots a black hole right out of its galaxy and sends it drifting into intergalactic space. No starry backdrop, no orbiting gas, no grand accretion disk glowing like a cosmic neon sign, just a rogue black hole wandering through the dark, a silent gravitational beast that might go billions of years without anyone even noticing it exists. These are the stray black holes, unplugged vacuum cleaners roaming free across the universe with absolutely no supervision. To appreciate how bizarre that is, you have to remember that black holes are not exactly lightweight objects. A stellar mass black hole might weigh as much as several suns. A supermassive black hole can weigh millions or even billions of times more. Kicking one of these monsters out of a galaxy requires extreme gravitational drama, far more intense than anything that flings out rogue stars or lonely planets. Yet the universe has a habit of throwing dramatic events on scales that make human chaos look quaint. One of the leading ways a black hole gets ejected is through the cosmic equivalent of galactic bumper cars. When galaxies collide, and they do so more often than anyone intuitively expects, their centers may each host a supermassive black hole. As the galaxies merge, these central black holes spiral toward each other in a slow, hypnotic gravitational dance. If a third black hole happens to be pulled into the mix, a runaway from another galaxy, or a leftover from a previous merger, the situation becomes a gravitational triangle, with tension high enough to fling one of the participants outward at mind-bending speeds. The ejected black hole rockets out of the merged galaxy like a disgruntled coworker who quit during a meeting and left through the window instead of the door. But there is an even more spectacular mechanism, one that comes from the very fabric of space-time itself: gravitational wave recoil. When two black holes merge, they release gravitational waves, ripples in space-time that carry energy away. If the waves come off unevenly, the final merged black hole gets a sudden kick, a cosmic recoil that can send it hurtling out of the galaxy at thousands of kilometers per second. That is fast enough to leave even the most massive galaxies behind, drifting into intergalactic darkness with no chance of ever returning. Imagine being launched from your hometown so hard you leave the entire continent, the planet, the solar system, the galaxy, and then keep going indefinitely. Once a black hole is adrift in intergalactic space, it enters a phase so quiet it is almost eerie. Black holes do not glow unless they are actively feeding, and intergalactic space is far too empty to provide them with a decent meal. These rogue black holes become effectively invisible, silent gravitational scars drifting through the darkness. A passing atom here or there does not even come close to making them shine. They become predators in a wilderness with almost no prey, waiting billions of years for anything unlucky enough to cross their path. Despite their stealth, these stray black holes shape their surroundings in subtle ways. A wandering black hole tugs on any matter it encounters, altering the trajectories of dust, gas, or even drifting stars, if any happen to pass close enough. Over millions of years, these tiny nudges accumulate, creating faint gravitational fingerprints that astronomers might detect if they look closely enough. Some rogue black holes may still carry remnants of their past lives, tiny star clusters that got dragged out alongside them, orbiting the black hole like loyal companions who refuse to let it wander alone. These clusters can act as glowing signposts, revealing the presence of a dark monster hidden in their center. The idea of a supermassive black hole drifting alone in intergalactic space is especially dramatic. These giants once resided at the hearts of entire galaxies, anchoring billions of stars with their overwhelming gravity. Imagine a city waking up to find that its downtown skyscraper quietly walked away in the night. The galaxy it leaves behind continues on, but something fundamental has changed. The gravitational architecture shifts subtly. The dance of stars adjusts. Meanwhile, the ejected black hole moves deeper into the cosmic dark, leaving behind everything it once held together. Astronomers have found hints of these runaway giants, stars moving strangely fast, gas clouds showing odd distortions, and potential lone accretion flares in regions where no galaxy exists. These clues suggest that stray black holes might be far more common than we once believed. Some estimates propose there could be millions of them drifting through intergalactic space, each one invisible unless it happens to snack on a passing cloud or unlucky star. It is a chilling thought. The universe may be filled with silent, roaming singularities, gravitational traps wandering without warning signs, like pitfalls hidden in a dark forest. And yet, despite the drama surrounding their origins and the mystery of their travels, rogue black holes remind us just how wild the universe can be when it is left to its own devices. These are objects that once commanded entire galactic centers, now reduced to cosmic vagabonds. They are the universe's unplugged vacuum cleaners, roaming freely with no power cord, no outlet, and no chores to do, just wandering through eternity, quiet and unstoppable. Their existence paints the intergalactic vastness not as an empty stage, but as a realm where even the most powerful objects can lose their cosmic addresses and drift into anonymity. In a universe defined by movement, gravity, and constant change, even black holes can be uprooted. And when they are, they become some of the strangest travelers the cosmos has ever produced, silent wanderers roaming the darkness, carrying with them the echoes of galaxies they once called home. When you picture the darkness between galaxies, you might imagine a perfect, silent void, an expanse so black it swallows even the idea of light. But intergalactic space, despite its emptiness, hums quietly with radiation. Not bright, flashy, headline-grabbing light, but faint, stubborn leftovers from events long past. It is the universe's afterglow, a soft cosmic echo that refuses to fade completely, like the lingering scent of a campfire hours after the flames have died. This gentle radiation spreads across the intergalactic wilderness, whispering stories about ancient stars, long-gone galaxies, and cosmic events that took place before Earth was even a thought. One of the most haunting forms of this radiation is the extragalactic background light, a diffuse glow made from the leftovers of billions of stars burning across cosmic time. These stars lived, shone, died, and left behind a soft fog of photons wandering the intergalactic expanse. Most of these photons travel freely, never encountering dust, gas, or matter dense enough to swallow them. They just drift, as casually as dandelion seeds on a summer breeze, carrying with them the accumulated history of stellar evolution. The beauty of this background light is that it is both ancient and ongoing. Every star that has ever shone contributes to it. Every galaxy, no matter how distant or faint, adds its bit of light to the cosmic fog. Even the earliest generation of stars, those mysterious giants that lived fast and died young, may have sprinkled the intergalactic dark with their faint ultraviolet glow. Those primitive stars are long gone, but their photons continue their endless travels, outlasting even the memory of the worlds where they were forged. This radiation is faint, astonishingly faint. If you could somehow tune your eyes to see it directly, it would not be like switching on a cosmic nightlight. It would be more like noticing a whisper of brightness at the edge of perception, a suggestion of light, rather than actual illumination. Yet astronomers can detect this glow by studying how it interacts with more energetic particles. High-energy gamma rays traveling across the universe occasionally collide with photons from the background light, vanishing in tiny flashes that reveal just how much diffuse radiation fills intergalactic space. In a sense, those gamma rays are cosmic tourists complaining about the light pollution they encountered on their journey, allowing astronomers to map the faint glow through their interrupted travels. But the intergalactic radiation is not just starlight from long ago. The universe is awash with other kinds of faint, roaming energy. Some of it comes from quasars, those brilliant, distant beacons powered by ravenous, supermassive black holes. Quasars shine so fiercely that their radiation can travel across billions of light years and still leave fingerprints on intergalactic gas. Their photons wander far beyond their home galaxies, illuminating patches of the cosmic web with a light so ancient that by the time it reaches us, an entire galaxy might have merged, twisted, or completely changed its shape. There is also the glow of ionizing radiation, high-energy photons capable of stripping electrons from atoms. This kind of light has shaped the universe in profound ways. In the early epochs of cosmic history, after the first stars ignited, waves of ionizing radiation swept through the universe, turning the cold neutral gas into a warm sea of charged particles. That era, known as reionization, was like the universe switching from darkness to a faint cosmic dawn. The leftover traces of this radiation continue to fill intergalactic space, reminders of a time when the universe was transforming from a starless void into a luminous, evolving cosmos. And then there are the cosmic rays, hyperactive particles zipping across the universe with the enthusiasm of caffeinated marathon runners. These rays are not photons. They are charged particles like protons and atomic nuclei, launched by violent astrophysical events such as supernova explosions and black hole jets. While they cannot be seen like light, they contribute to the overall radiation environment in intergalactic space. They pepper the void with energy, occasionally smacking into stray atoms or dust grains, creating cascades of secondary particles that ripple through the darkness. It is like the universe tossing occasional sparks into an otherwise quiet room. All these forms of radiation add up to something profound. The universe is never truly dark. Even the emptiest regions contain a faint haze of light, energy, and particles that have traveled unimaginable distances. The intergalactic void is less of a blank slate and more of a cosmic attic filled with subtle traces of everything that has come before. It is filled not with immediate brightness, but with the accumulated glow of cosmic history. These faint afterglows serve as invaluable tools for astronomers. They help measure how matter is distributed, how galaxies evolved, and how energetic events shaped the intergalactic medium. When a photon from a distant star gets absorbed or scattered by something in intergalactic space, it leaves a tiny clue, an imprint on its spectrum that can be read like a cosmic timestamp. By studying these clues, scientists reconstruct a long and intricate narrative of how the universe built itself up over billions of years. In a poetic way, this radiation reminds us that nothing in the universe fully disappears. Stars fade, galaxies drift apart, cosmic events become ancient memories. But the light they once released continues on, quietly filling the intergalactic darkness with the faintest glow. The universe carries its history not only in the galaxies we can see, but also in the subtle afterglow that lingers everywhere, whispering the story of a cosmos that refuses to let its past slip entirely into the dark. If the universe had a category for most hyperactive traveler, cosmic rays would win by a landslide. These particles do not drift, stroll, or wander. They sprint. They rocket through intergalactic space with the kind of reckless enthusiasm normally reserved for kids who just discovered sugar. Cosmic rays are charged particles, mostly protons, with a scattering of heavier nuclei that have been launched into the universe by extremely energetic events. And when they travel between galaxies, they do so with zero chill, zooming across distances so huge they turn entire clusters of galaxies into their personal obstacle courses. What makes cosmic rays especially wild is how fast they move. Some cosmic rays travel at speeds close to light itself. Not metaphorically close, literally close. If they went any faster, they would need a private meeting with Einstein to discuss the implications. At these extreme speeds, time begins to stretch and distort. From the particle's point of view, its entire journey, spanning millions or even billions of years, might feel almost instantaneous. Imagine sprinting across the universe and arriving before your cosmic playlist even finishes its first song. But what launches these particles with such absurd energy? The universe has a few favorite mechanisms, and none of them are gentle. One common accelerator is a supernova explosion. When a star explodes, it blasts shock waves outward at tremendous speeds, sweeping up surrounding gas and dust. These shock fronts behave like natural particle launchers, whipping charged particles to unimaginable energies. If planets had fitness trainers, supernova shockwaves would be the ones shouting motivational slogans like, "Feel the burn," except the burn is the laws of physics being tested to their limits. Even more extreme are the jets produced by active galaxies, those cosmic engines driven by supermassive black holes feeding on surrounding matter. When material spirals into a black hole, intense magnetic fields can twist and fling particles outward in narrow, powerful beams. These jets can stretch for thousands of light years, acting like cosmic railguns that shoot particles deep into intergalactic space. A cosmic ray born in such a jet starts its life not with a gentle nudge, but with a furious shove from a black hole that is too busy devouring matter to worry about collateral effects. Once cosmic rays are launched into intergalactic space, their journeys become long, chaotic, and unpredictable. Because they are charged particles, cosmic rays do not travel in straight lines. They zigzag wildly through the cosmos, swayed by magnetic fields that thread between galaxies. Even faint, weak magnetic fields, one so subtle that stars barely notice them, can twist the paths of these particles, turning their trajectory into a cosmic scribble. By the time a cosmic ray reaches a new galaxy, it may have traveled a route so convoluted it looks like a toddler drew it during a sugar rush. Despite their frantic motion, cosmic rays rarely interact with anything in intergalactic space. The void is simply too empty. A cosmic ray might travel millions of light years before encountering a single atom. When interactions finally do happen, they can produce bursts of secondary particles or faint glimmers of high-energy photons. These interactions reveal where cosmic rays have passed, like footprints left by someone sprinting across a snowy field. Astronomers study these subtle clues to understand how cosmic rays travel, what accelerates them, and how they contribute to the overall energy budget of the universe. One of the most astonishing aspects of cosmic rays is how much energy they can carry. The highest energy cosmic rays have more energy than a fast-pitched baseball. That might not sound impressive until you remember that all of this energy is packed into a single subatomic particle trillions of times smaller than the baseball. If you ever feel unproductive, remember that somewhere in the universe, one proton is traveling with the energy output of an entire sports moment, and it is still not entirely sure where it is going. Cosmic rays also play a subtle but important role in shaping the environments they travel through. When they eventually collide with gas or dust, they can ionize atoms, trigger chemical reactions, and influence how gases cool or heat. In galaxies, cosmic rays help regulate star formation by adding pressure to gas clouds. In intergalactic space, their influence is gentler but still significant. They contribute to the faint energy permeating the void, affecting how particles behave over enormous distances. These particles also carry information about the places they came from. Their composition, energy, and direction all whisper clues about their birthplace. Scientists studying cosmic rays are like detectives chasing suspects who sprinted through 10 different cities, changed disguises several times, and somehow still left tiny clues behind. Decoding those clues helps reveal the nature of the powerful astrophysical events that created them. Detecting cosmic rays is challenging because the particles themselves do not politely line up for inspection. Instead, scientists watch for the showers of secondary particles created when cosmic rays slam into Earth's atmosphere. These showers cascade downward like invisible fireworks, producing fleeting signals that can be captured by ground-based detectors. Observatories scattered around the world monitor these particle showers, trying to reconstruct the original cosmic ray's energy and path. It is like trying to identify a speeding car by looking at the gravel it kicked up 3 miles down the road. And what about cosmic rays that never reach galaxies? Many spend eternity between them, trapped in the vast expanses of intergalactic space. They keep sprinting, looping, twisting and tumbling in response to magnetic forces. They age without slowing, race without resting, and roam without destination. They are the universe's most restless travelers, particles in a perpetual marathon across a course measured in light years. In the grand tapestry of the universe, cosmic rays are tiny, energetic messengers that refuse to sit still. They sprint across intergalactic distances with boundless enthusiasm, carrying stories of exploding stars, ravenous black holes, and cosmic violence across billions of years. They are proof that even the smallest particles can have the wildest journeys, and that in the quiet darkness between galaxies, something is always racing by with absolutely no chill. If the universe were a grand theatrical performance, galaxies would be the dazzling actors, spinning, glowing, colliding, and occasionally throwing million light-year tantrums. But every great show relies on a backstage team working tirelessly behind the scenes, quietly arranging props, lifting scenery, and making sure nothing falls apart. In the cosmic drama, that invisible crew is dark matter. It surrounds galaxies in vast, unseen halos, stretches between them in long, delicate bridges, and fills intergalactic space with a silent presence so persistent and so influential that without it, the universe's entire performance would collapse into an unrecognizable mess. And true to form, dark matter does all of this without ever stepping into the spotlight or asking for the smallest amount of applause. Dark matter is one of the most mysterious ingredients in the cosmos, not because it hides, but because it refuses to interact with light. It does not glow, reflect, absorb, or scatter photons. Shine even the brightest laser at it, and dark matter would shrug and keep walking. Its invisibility is so complete that if it could talk, it would probably insist, "I'm not mysterious, you're just using the wrong eyes." And yet, despite its refusal to play by the normal rules of detection, dark matter reveals itself through gravity. Wherever dark matter gathers, it creates gravitational wells that shape the motion of galaxies and the structure of the entire cosmic web. Intergalactic space, far from being an empty desert, is threaded with dark matter filaments, long ghostly highways that stretch across millions of light years. These filaments act like scaffolding for the visible universe. Galaxies cluster along them, sliding toward denser regions as if following well-worn paths carved by an invisible hand. Without these dark matter filaments, galaxies might still form, but they would be scattered and disorganized, drifting like lost islands with no underlying structure to guide their motion. Instead, dark matter provides the blueprint the universe has followed for billions of years. These filaments are not delicate strands, but enormous structures made of countless dark matter particles, each obeying gravity with perfect discipline. They pull on one another, accumulate mass, and exert gentle but persistent influence on anything that drifts nearby. Even though the visible matter, stars, gas, and dust, is only a small fraction of the total mass, it ends up decorating the dark matter skeleton like lights strung on an invisible tree. If dark matter were suddenly removed, galaxies would fly apart. galaxy clusters would unravel, and the cosmic web would collapse like a tent whose stakes were yanked out all at once. The true strength of dark matter becomes clear when looking at galaxy rotation. Stars far from a galactic center move much faster than they should if only the visible matter were there. It is as if galaxies are spinning too hard for their own good, but refuse to fly apart. Something massive and unseen holds them together, something forming a vast halo of gravitational support. That something is dark matter, quietly tightening the cosmic bolts while the galaxy performs its spinning routine. These halos extend far beyond the visible edges of galaxies, sometimes stretching hundreds of thousands of light years into intergalactic space. In these outer regions, dark matter dominates completely, forming smooth, spherical cocoons that cradle each galaxy in a gravitational embrace. Galaxies moving within clusters are not interacting directly with the space between them. They are interacting with the overlapping halos of dark matter that permeate the region. The cluster becomes a buzzing community of invisible spheres, each influencing the motion of its neighbors. From the outside, it looks like galaxies dancing, but really, the choreography comes from the stage crew in the shadows. Dark matter also plays a subtle but vital role in how galaxies grow and evolve. As material flows along dark matter filaments toward dense regions, it forms new stars, builds up galactic disks, and feeds the massive structures at the universe's deepest intersections. When small galaxies approach larger ones, dark matter halos feel the pull long before the visible material reacts. It is the halos that begin the gravitational handshake, setting the stage for future mergers and cosmic rearrangements. In this way, dark matter acts like a silent matchmaker, pairing galaxies long before they ever physically touch. One of the most astonishing facts about dark matter in intergalactic space is that it outweighs visible matter by a tremendous margin. For every particle of ordinary matter drifting between galaxies, there could be 5 times as much dark matter quietly passing through. And because dark matter interacts so weakly, these particles do not collide or clump the way normal matter does. They glide through one another effortlessly, forming giant diffuse structures that influence everything but are seen by nothing. Astronomers map these invisible structures by studying how they bend light from distant galaxies. This bending, called gravitational lensing, acts as a cosmic fingerprint pattern left by the dark matter's gravity. When we examine these distortions, we see the hidden shape of enormous dark matter networks spanning the intergalactic void. The picture that emerges is not a random scattering of invisible mass, but a carefully arranged system of threads, knots, and bridges holding the universe together with quiet precision. Dark matter's greatest accomplishment might be its role in shaping galaxy clusters. These clusters, the largest gravitationally bound structures in the universe, are filled with galaxies orbiting a common center, like bees circling a hive. But the true anchor of a cluster is not the galaxies themselves. It is the massive cloud of dark matter sitting at its core. Without that invisible mass, the galaxies would not stay bound. they would drift apart, carried away by their own inertia. Instead, they remain gathered, held in place by a dark, unseen gravity that is far more powerful than anything the visible matter can provide. If the universe were a stage play, the actors would shine under bright lights, dazzling the audience with their brilliance. But behind them, in the shadows, the stage crew, quiet, tireless, invisible, would be doing the real work. Dark matter is that crew, guiding the movements, setting the stage and shaping the cosmic performance from behind the curtain. It never asks for applause. It never tries to be seen. It simply holds the universe together, one invisible halo at a time. Intergalactic space already feels like the universe's version of minimalism. Barely any atoms, almost no stars, long stretches of quiet darkness, and the occasional rogue object just passing through. But what if the emptiness is not quite as empty as we think? What if the spaces between galaxies, vast as they are, harbor things we have hardly imagined yet? Every time astronomers point their instruments into the dark, they discover some new sliver of unexpected reality. And while much of intergalactic space is filled with well-understood components like thin gas and dark matter, there is room, vast room for speculation. After all, the universe is not short on surprises. It has a habit of saying, "Oh, you thought you understood me? That's adorable." One tantalizing possibility is the existence of intergalactic molecules. At first, that sounds almost absurd. Molecules require atoms to bond, and atoms in intergalactic space are so thinly spread they make even the loneliest hydrogen seem outgoing. And yet, conditions could occasionally line up just right for a few atoms to form a molecular bond. Hydrogen molecules, in particular, are the simplest structures that could arise. Two hydrogen atoms linking hands in a place where hand-holding is ridiculously rare. These molecules would be fragile, vulnerable to ultraviolet light, and constantly at risk of being torn apart by the faintest hint of radiation. But if they managed to survive, they could drift for unimaginable distances, acting like tiny messages in cosmic bottles, each carrying clues about the environments they've passed through. The rarity of these molecules does not make them unimportant. Even a few stranded molecular structures could help us probe the temperature and density of the intergalactic medium in new ways. Detecting them would be incredibly difficult, like trying to hear a single violin note inside a stadium during a rock concert. But if found, they would open a window into the cold chemistry of the cosmic wilderness, chemistry that unfolds not in vibrant nebulae or bustling star-forming regions, but in the quietest, darkest reaches of space. Beyond molecules, some scientists speculate that intergalactic space might play host to exotic particles, forms of matter that do not fit comfortably among protons, electrons, or even the ghostly dark matter we have acknowledged but cannot see. Exotic particles could include things like sterile neutrinos, hypothetical particles that interact so weakly with ordinary matter they make dark matter look chatty by comparison. If they exist, sterile neutrinos could drift through intergalactic space in enormous quantities, leaving no direct trace except maybe the whisper of their decay products. Detecting them would require instruments of incredible sensitivity, and even then, the clues might be faint. tiny distortions in cosmic radiation, slight irregularities in the distribution of matter, or faint X-ray lines that do not match known atoms. Other exotic candidates include axions, hypothetical particles proposed to solve certain mysteries of particle physics. If axions exist, they might be produced in vast quantities in the early universe and now fill intergalactic space like a thin, invisible mist. Under certain conditions, axions could convert into photons when they pass through magnetic fields. That means intergalactic space, threaded with faint magnetic structures, could act as a giant laboratory where axions flicker in and out of detectable states. The thought is speculative, but not absurd. If axions are real, the cosmos might be flashing with signals we have not yet learned how to interpret. Beyond particles, there are even more speculative possibilities, hypothetical compact objects drifting through the void. These would not be stars or planets or black holes. We've covered those. Instead, imagine objects made of strange forms of matter. Quark nuggets, for instance, are theoretical clumps of ultra-dense material formed in the universe's earliest moments. These nuggets, if they exist, could be heavier than mountains but smaller than marbles, drifting silently between galaxies like lost cosmic relics. Their surfaces might be so dense that ordinary matter barely interacts with them, glancing off like raindrops hitting steel. A single quark nugget could pass through an entire galaxy without leaving so much as a dent. Another speculative idea involves primordial black holes, tiny black holes that could have formed shortly after the Big Bang, long before stars existed. These black holes might be smaller than mountains or the size of asteroids, quietly zipping around the universe as miniature gravitational pinpoints. If they exist, intergalactic space would be the perfect environment for them. No stars to devour, no gas to heat, no galaxies pulling them into orbits. They would simply drift silently, each one a tiny wrinkle in the fabric of space-time, detectable only if it happened to pass in front of something bright and briefly distort the light. And then there is the possibility, still cautious, still hypothetical, that intergalactic space might harbor forms of matter or energy we have not yet conceived of. The universe has never hesitated to surprise us. Once upon a time, galaxies themselves were unknown. Then dark matter, then dark energy. Each discovery rewrote our understanding of what the universe even means. If history is any guide, the cosmos is far from finished with its plot twists. It is tempting to imagine entire families of unobserved objects drifting between galaxies. Cold, faintly glowing clusters of exotic matter, tiny pockets of unknown forces, even compact structures built from physics that has not yet been written. These possibilities are not predictions. They are invitations to curiosity. They challenge us to ask better questions, to build sharper instruments, and to keep reminding ourselves that the universe is not obligated to be simple. It is only obligated to be itself. In the end, the speculative possibilities hidden in intergalactic space remind us of the joy of scientific imagination. They invite us to stretch our minds into the unknown, to blend grounded evidence with open wonder, and to imagine what might be lurking just beyond the edge of our detection. The universe is wide, strange, subtle, and ever-evolving. and the spaces between galaxies may still hold entire chapters of cosmic history waiting to be uncovered. If you began this journey imagining the space between galaxies as a silent, empty void, you now know the universe had other plans. It turns out that nothingness is terrible at being nothing. The intergalactic wilderness, so vast, so dark, and so blindingly empty at first glance, is actually alive with stories, processes, and wanderers that defy the simplistic idea of a cosmic vacuum. It is a realm where invisible scaffolding shapes the architecture of everything we see, where drifting atoms carry ancient histories, and where lonely travelers journey across distances so extreme they challenge the limits of imagination. The space between galaxies is, quite ironically, the place where the universe reveals some of its most intricate behavior. It is almost comedic how the cosmos hides so much in a region we routinely describe as empty. The universe seems to have a sense of humor about this, like someone insisting their backpack is light while quietly carrying a bowling ball. Take even a casual look at the intergalactic dark, and you begin to see the layers, the faint glow from stars that died before Earth existed, the flicker of radiation wandering across space-time, the energetic particles sprinting wildly in every direction, and the invisible halos that cradle galaxies like unseen guardians. Even the weakest structures, so subtle they barely rise above nothingness, play roles in shaping the universe's grand design. In a way, intergalactic space is the universe's backstage area. Not because it is hidden, but because it is where the real work happens. Galaxies often take center stage, bright, spinning, noisy with starlight, but between them lies the quiet infrastructure that holds the cosmos together. Gravity stretches its hands across these vast distances, molding matter into threads and filaments. Dark matter, quiet and persistent, forms the skeleton that galaxies drape themselves over. Faint gases drift through the gulf, heating, cooling, and whispering tales of events that happened billions of years ago. Even dust grains, tiny, stubborn survivors, wander across the dark like tourists who refuse to let an entire universe stop them from exploring. And occupying this wilderness are the renegades, the misfits, and the cosmic wanderers. Planets without stars drifting into oblivion, but somehow continuing their journey. Stars flung from their galaxies with such enthusiasm that they spend eternity wandering the dark. Black holes launched from their homes by gravitational drama, silently sliding through intergalactic space like unplugged vacuum cleaners that escaped the closet. These objects remind us that the universe does not run on tidy or predictable rules. It runs on motion, energy, chaos, and long, slow change, much of it unfolding far from the bright places we most easily notice. The most astonishing thing about the intergalactic void is not that it hides so much, but that it connects everything. Its vastness forces us to view the universe not as scattered islands of activity, but as an interwoven whole. The darkness between galaxies is threaded with the same forces that guide the galaxies themselves. It is not an absence, but a medium, a sprawling cosmic highway where particles race, light drifts, and gravity subtly shapes the future of everything. This expanse also humbles us. It shrinks our sense of what empty means and expands our imagination for what might still be out there. The universe has never been shy about surprising us. Every time scientists point new instruments at intergalactic space, they uncover something unexpected, a hint of unaccounted energy, a faint structure too subtle for earlier telescopes, an unknown signal that demands a new theory. It is in the darkness that the cosmos reveals its wildest secrets. Emptiness is not a void. It is a canvas on which the universe paints quietly. The more we learn about intergalactic space, the more it feels like a reminder that the universe does not need constant brightness to be alive. It breathes through the slow drift of atoms, the whisper of radiation, and the invisible pull of gravity. It speaks through the movements of objects that have no homes and the persistence of particles that refuse to stop racing. It contemplates through long epochs where change happens in spans too vast for human eyes, but too important for cosmic history to ignore. So when we talk about the space between galaxies, we are not describing nothing. We are describing a realm that hosts the echoes of ancient stars, the fingerprints of cosmic structure, and the pathways of objects wandering freely across eternity. This is the universe's quiet heartbeat, steady, subtle, and impossible to silence. Perhaps the most poetic truth hidden in all this is that emptiness, when examined closely, becomes full of meaning. The intergalactic dark teaches us that the universe does not measure richness by brightness or density. It measures it by the interplay of forces, the endurance of particles, and the astonishing complexity woven into even the thinnest traces of matter. It shows us that profound things often happen far away from the spotlight. In the end, the space between galaxies is not a lonely void. It is the universe's most expansive frontier. It is the silent sea where the faintest signals travel, where the grandest structures take shape, and where cosmic wanderers drift endlessly through the dark. It is the place where nothingness reveals its busy schedule, proving that even the quietest corners of the cosmos are filled with stories waiting to be discovered.